Alright, hello there. My name is Declan and today I'll be talking a bit about sparse matrices and particularly how they are implemented in Matlab. So, if you're watching this, I imagine you are familiar with the concept of sparse matrices. They are matrices with relatively few non-zero elements, like say this poorly drawn identity matrix over here. It has 3 non-zero elements and then 6 elements all equal to 0, definitely making it sparse. That being said, there's not actually a fixed definition for sparse matrices. There's no clear distinction between where sparse matrices start and dense matrices end. One definition says that the number of zero elements must be more than the number of non-zero elements, like say is the case in this identity matrix over here, suggesting we should have a density of 50% or less. But for many applications, this density is still very high. Another approach is to say that the number of non-zero elements should be order of the number of rows or columns, suggesting that larger matrices should have smaller densities than smaller matrices. But also for particular implementations, this may not be a particularly useful definition. Now, a definition that I encountered, which I really like, is one by James Hardy Wilkinson. He was a prominent numerical analyst in the previous century who said that sparse matrices is any matrix with enough zeros that it pays to take advantage of them. Now, of course, this definition is not particularly helpful. It does not tell us what makes a sparse matrix, or at least what density, for example, makes a sparse matrix. But it does illustrate exactly why we're talking about sparse matrices in the first place. That is, if we can exploit the zero elements within the matrix, then we should definitely do so. And then at that point, it makes sense to call the matrix sparse, independent of how sparse it actually is. Now, if we're talking about advantages of sparsity, there are really two main advantages that we're talking about. First of all, we don't have to operate on all the zero elements. That is, we know that 0 times x is always going to be 0, and 0 plus x is always going to be x. So therefore, we really don't need to perform these operations. We already know their result. So this could save us computational time and effort. Now, since we're not performing these operations on sparse matrices, there's also really no need to store these zero values in the first place. So by not storing these zero elements, we can save a lot of computer memory in cases where we have very big and very sparse matrices. Now, obviously, this does come at a cost. And in particular, this cost is that we're dealing with a more complicated data structure. That is, if we're storing only the non-zero elements of a sparse matrix, then we do need to know where these non-zero elements are actually located within the matrix itself. So storing this additional indexing information is going to require extra memory, and therefore, if our matrix is too full, this additional indexing information may actually cost us more memory than it saves, meaning that this second advantage just drops away completely. Similarly, if we're performing operations like matrix multiplication, in doing so, we will need to check where the non-zero elements are located and to perform the correct operations. And checking this will also require computational effort, meaning that this first advantage may also drop away completely if our matrix is too full. So we can exploit sparsity. We do so in many cases, but of course it's only worth it if our matrix is actually sparse. Now, in such a case may appear, for example, when we're implementing polynomials in Matlab. Now, something that I'm working on right now is the dpvar. This is an alternative representation for polynomials in Matlab, where we're separating decision variables, say d1, d2, d3, and d4, from polynomial or independent variables, say x and y. Now, in doing so, we introduce two monomial vectors, monomial bases. So z1 is a monomial in the independent in the decision variables, where we note that the decision variables can only appear linearly, so they cannot be multiplied and they cannot be raised to any power. Now the polynomial variables, they can be multiplied and they can be raised to powers, which is what separates them from the decision variables in the first place. Then to connect each decision variable to a particular monomial, we use this coefficient matrix C over here. So for example, for this 2 by 2 polynomial over here, this coefficient matrix C is divided into 2 by 2 blocks, where say this top left block is associated with this top left element, and similarly these other blocks are associated with the other elements. Then to describe, for example, this top left element, we note that we need to multiply the decision variable d1 with the constant value 1, for which we have this non-zero located over here. To describe the second term, we need to multiply the constant value 1 with the polynomial variable x, for which we have the non-zero value 1 over here. Similarly, for the other elements, we also need to associate one particular decision variable with a particular monomial, for which we have the non-zero elements within each block. And then if we look at the matrix as a whole, we note that we really only have 5 non-zero elements here in a 10 by 10 matrix, making this matrix definitely sparse. Of course, this is just one particular example of a polynomial involving decision variables, where this particular approach, this particular description of the polynomial works quite well, and we end up with a sparse coefficient matrix. But you can imagine that in many situations, describing the polynomial in this dpvar format, we're gonna encounter a sparse coefficient matrix C, which is why we're also implementing the coefficient matrix C as a sparse matrix in Matlab. Now that's actually why I'm talking about sparse matrices in the first place. In describing these coefficient matrices, in working with them in Matlab, we're trying to do so in the optimal manner, which is what I've been looking into over the past few weeks. In particular, I've been looking at how we should work with sparse matrices by first looking at how sparse matrices are stored in Matlab, and then based on that, look what this tells us about manipulating sparse matrices in Matlab. And that's exactly what I'm going to be talking about today. Now, brief disclaimer there, I'm not actually an expert on computer science. I will not be informing you of the best way of working with sparse matrices in Matlab or in any other program. All I will be telling you is how these sparse matrices are actually implemented in Matlab and what this tells us about working with them. I'll be giving some advice on things to do and things not to do. But other than that, it will really depend on the particular problem that you're working on. What is the quote-unquote best approach? Now, before we can establish how sparse matrices are stored, it's important to know what memory actually looks like. So memory in a computer is actually a linear object. That is, it's defined by a single index or address. So really, memory is just a long string of bits, where each set of 8 bits forms a byte, and then a certain set of bytes can be used to store a value. So say, for example, we want to store the value of pi, then we can store this as a double precision floating point number, requiring 8 bytes of data. So for example, we can store it within this block over here. Now say that instead we want to store an array of numbers like pi, 1, square root of 2, and 3. Then this is going to require 4 of these blocks. So for example, we can start over here with index 1001, ending with 1008 to store the value of pi. Then use 1009 up to 1016 for number 1, 1017 up to 1024 for the square root of 2, and 1025 up to 1032 for the value of 3. So in this way, arrays are stored basically as arrays in memory as well, where each value is assigned a certain block and then a bunch of blocks in a row can be used to store a one-dimensional array. However, if we move to two-dimensional or higher dimensional objects, we're going to run into a problem, of course, because these still need to be represented as a 1D object in memory. So in doing so, there are really two major choices. You can probably guess them. They are column major order or row major order. Now in column major order, what we're doing is we're storing this object one column at a time. So we start here with the first column, storing 11, 21, 31, and then 41. And then we move on to the second column, storing the values 12, 22, 32, going forth until we get to this final column and the final value of 44. Now, if this is how we store it in column major order, obviously storing it in row major order, we're doing the same thing, but now row by row. So we start storing the value 11, then 12, then 13, then 14, then comes 21, 22, 23, 24, continuing in this manner until we get to our final elements of 44 again. Now, why am I telling you this? Because this column major order or row major order is a big decision. It has quite a bit of influence on how other operations are performed as well. Matlab has chosen to use this column major order, so does Fortran, but codes like Python and C, they actually use row major order. So in this sense alone, these languages are quite different. Now, what does this mean for sparse matrices? Well, when we're talking about sparse matrices, we have to make a similar choice, of course. They are two-dimensional objects. The only difference is now we are excluding these zero elements. So we're still storing the non-zero elements, but these zero elements are no longer stored. But in storing these non-zero elements, we can still make a choice of either column major order or row major order. So in column major order, we store it one column at a time, meaning the array would look like this, starting with 11 and 21, then comes 42, then 23 and 33, and then finally the value 14. Whereas in row major order, we would start with 11, then 14, then 21, 23, 33, and 42. Now, in sparse matrices, of course, we also need to indicate where the non-zeros are actually located. Since, for example, from this information, it's impossible to derive where, for example, this value 11, is actually located within the object, since we are excluding zeros. So to do this, we need indexing information. And this indexing information can be stored in several different ways, actually. So for example, we can store it using a dictionary of keys. So a dictionary is just a collection of keys, where in this case, each key is, for example, a row index and a column index, say 1, 1. And then each key is associated with a certain value, in this case, the value 11. Then the key 2, 1, so row 2, column 1 would be associated with the value 21. Key 3, 3 would be associated with the value 33, and so on and so forth. So you can see that storing this matrix in a dictionary of keys kind of way, we are actually directly relating the column and row indices with their values. So there's no need to actually perform a column major or row major order, since they are all stored as separate objects. That being said, this also means that this is not a particularly efficient approach when you're performing arithmetic operations, since all the values are stored separately. Now, a similar approach would be a list of lists. In this approach, we can store, for example, one row at a time, starting with this first row, where we have only the non-zero values 11 and 14. And then for these values, we also need to indicate in what column they are located. So in this case, column 1 and 4. Now for the second row, we do the same. We store only the non-zero values 21 and 23. And then we indicate that these are located in columns 1 and 3. Now going on, we store basically the full array using a bunch of rows with for each row a column index. Now, a third approach, and perhaps, or at least in my opinion, the most obvious approach for storing these sparse matrices is storing 3 arrays. So we start with the actual non-zero values. So that would be 11, 21, 42, 23, 33, and 14. And then for each value, we also indicate the row in which it is located and the column in which it is located. So 11 is located in row 1 in column 1, 21 is located in row 2 in column 1, 42 in row 4 in column 2, etc. So in doing so too, we don't really need to adhere to any particular order. We don't need to use row major order or column major order, so long as each non-zero element is associated with the proper row number and column number. But it can still be useful for purposes of, well, numerical efficiency to order them in a particular way. Now, Matlab actually uses neither of these 3 approaches. What Matlab does is use a compressed sparse format. So the compressed sparse format is actually a very common way for storing sparse objects. But here too, we can make a choice, either a compressed sparse column format or a compressed sparse row format. So in both formats, we store the number of all the non-zero values in a value array. But in the first, we store it in a column major order, and in the second, a row major order. So we can see here, if we store the values in this compressed sparse column format, you see that the first column is located over here, 11 and 21. The second column is just the value 42. The third column is 23 and 33. And our final column is just 14. Now these are all stored together in one column, but you can see that they are stored, in fact, per column. So it's just one array of all the values, but it is stored kind of per column. Now, since we are storing it per column, we do need to indicate in which row each object, each non-zero value is located. So for that, we have a second array, the row index array, indicating that value 11, for example, is located in row 1, value 21 is located in row 2, value 42 is located in row 4, etc. However, instead of a column index, we use a column pointer now to indicate columns. Now, since we have stored our value array per column, basically, so we've concatenated all the columns below one another, we know that none of the columns will be mixed up. So we can indicate exactly where each column is going to start. So for example, our first column of our object in the value array is going to start with the first element. And that's where this column pointer 1 comes from. Then the second column of our object, just the value 42, within the value array is going to start at the third position, as you can see. So it's still just one array, but in the third position, we know our second column is going to start. And that's where this number 3 comes from. Now, in the fourth position, our third column already starts. So the third column is going to start in the fourth position, which is where this 4 comes from. And then finally, our fourth column is going to start in the sixth position, right over here. So note, we are using just 3 arrays. This value array is one object in memory, but we use this column pointer to indicate where in this array each column starts, noting that the column numbers, the column values are located together. These objects, these non-zero values, all correspond to the first column, these to the second column, these to the third column, and these to the fourth. So all we need to do is indicate where each column starts within the value array. And that's what these pointers are for. Now you can see there's actually an additional value right at the end. In Matlab, this corresponds to the number of non-zero values that we have. So you can see we have 1, 2, 3, 4, 5, 6 non-zero values in our object. So we add a number 6 at the very end of our column pointer. Other approaches may actually add an additional value 1 over here. So this would be 7 instead of 6. But in Matlab, we don't do that. We just store the number of non-zeros at the very end. Now, if we can do this in a compressed sparse column format, obviously we can also do so in a compressed sparse row format. In this case, we would store the value in a row major order. So we start with the first row, 11 and 14. Then comes the second row, 21 and 23. Then comes the third row, just 33. And then comes the fourth row, just 42. Now for these, we give a column index. We indicate in which column each non-zero value is located. So for example, the value 21 is located in the first column. The value 33 is located in the third column. And then instead of a column pointer, we give a row pointer. We indicate that our first row is going to start with the first element of this value array. Our second row is going to start with the third element of our value array. Our third row is going to start with the fifth value of our array. And then the fourth row is going to start with the sixth element of our value array. Now note that if, for example, let me get rid of this value did not exist, so this would be a 0 value, then in this case, this full column would be 0. So then in the column pointer, for example, we would indicate that our first column is going to start with value 1, but now this value of 42 is going to disappear. It's no longer going to be there, neither is this row index. And then our second pointer is going to indicate that our second column is going to start in the third position. However, we don't have a second column. Our second column is just 0, so it's empty. So really our third column is also going to start in the third position, meaning that our column pointer is going to look like this here, where we have 1 to indicate that our first column is going to start over here, 3 to indicate that our next column is going to start over here, 3 again to indicate that actually the third column is starting over here, and then 5 to indicate that our final column is going to start right over there. Okay, so that's it for the compressed sparse format. Once again, there's a big choice, compressed sparse column or compressed sparse row. Matlab uses compressed sparse column. So does Julia, actually. And in languages like Python, you can choose what kind of sparse structure you want to use. So you can choose to use this row format or this column format or this dictionary key or list of list or coordinate list, depending on what your implementation looks like. So you can actually switch between different formats if you like. So what does this mean for the memory? So how much does this storage save us? Well, let's say that A has NC columns, NR rows, and NNZ non-zeros. Then we note that our value index is always going to contain NNZ elements because it contains all the non-zero values that we have. Similarly, the row index is also going to contain NNZ elements because for each of our non-zero values, we have to indicate a row index. A column pointer, however, can be both longer or shorter, depending on the situation. Namely, for each column, it's going to have to indicate where it starts within our value and row index, which means that we have NC elements over here, plus the additional 1 value corresponding to the number of non-zeros. So this array is going to have a length of NC plus 1. Now in Matlab, each value is by default stored as a double precision floating point number, which is going to cost us 8 bytes of memory, meaning that this array is going to cost us 8 times NNZ bytes of memory. Now the row index and column pointer, these are stored as integers. However, it seems that in Matlab, these integers are also stored using 8 bytes of data, meaning that these arrays too are going to cost us 8 bytes per element. Now, if we compare this to the full storage, we note that in the full storage, we only store one array, namely the values. However, in this case, we also store the zero values, and these zero values are going to cost the same 8 bytes of data that the non-zero values are going to cost us. Meaning that it's going to cost us 8 times NC times NR bytes of data to store this object in full manner. Now, if we compare this, we note that the sparse storage is going to cost us this, where remember N and Z is the number of non-zeros, NC the number of columns, whereas the full storage is going to cost us 8 times NC times NR bytes of data. So that tells us that the sparse matrix storage in Matlab is cheaper whenever the number of non-zeros is less than this value over here. Now, it's not a particularly pretty expression, but for very large matrices, which is generally when you use sparse structures, this suggests that the density of our objects, so the number of non-zeros divided by the total number of elements, should be less than 1/2, which I suppose is a reasonable bound for when this sparse storage should be cheaper than the full storage. Now, another important consequence to note here is that this expression, the memory that it costs us, does not depend on the number of rows in our object. It does depend on the number of columns, but the number of rows does not appear anywhere. Now, what this means is that if we add 0 rows to our object, so rows with no non-zero values, this is not going to cost us additional storage or additional memory. However, if we add 0 columns to our object, that is going to cost us additional memory, simply because this column pointer will need to grow with the number of columns. Now, to illustrate this, here's a very simple test. So say that we store a 1/1 scalar value of 1 in a sparse format in Matlab. Then we need to store the value, of course, which is just the value 1. We need to store the row index. Since it's a 1/1 object, this is just going to be 1. We need to store a column pointer. Now, since we just have one object here, one value here, this is just going to be column 1. And then also the number of non-zeros, of course, which is this final value, which is also just 1. Meaning that we need to store 4 values in memory, each costing 8 bytes of data, totaling to 32 bytes. Now say now that instead of a 1/1 object, we want to store a 100/1 object, where the first 99 rows of our column vector basically are all 0, and then the final row contains a non-zero element 1. Now in this case, we still need to store one non-zero value, namely 1. The row index of this value is going to be 100, since it's located in the 100th row. But since we have one column, the column pointer is still going to be just 1, and the number of non-zeros is also still going to be just 1, meaning we still need to store just 4 values in our memory, each requiring 8 bytes, still totaling to 32 bytes. However, say now that instead of storing this column vector, we store an equivalent row vector, so the transpose of this object, as a 1/100 array. Then we note that we still need to store just one non-zero value, 1. The row index is going to be 1, since we have only one row. But now our column pointer is going to have the length of the number of columns, which is 100. So even if each value is going to be 1, we need to store 100 of these values, all equal to 1, as well as, of course, the number of non-zeros at the very end. Meaning we get 100 times 8 bytes, which is where the 800 bytes of data, in addition to the 24 bytes associated with these final 3 values. So what you see here is that storing this row array, this row vector, is going to cost us 824 bytes of data, whereas storing the equivalent column vector is going to cost us just 32 bytes of data. Now, of course, in practice, you'll not be working with vectors, sparse vectors, Usually you'll be working with sparse matrices instead. So this problem will not be as big, but it's always useful to keep in mind that Matlab stores its arrays in this compressed sparse column format. And that means that it prefers very large skinny matrices, so with few columns but many rows, over fat matrices with lots of columns and few rows. So that's always important to keep in mind, especially when working with sparse matrices. All right, so that's it for the memory. We now know how these sparse matrices are stored. What does this tell us about manipulating sparse matrices? Well, first of all, how can we build a sparse matrix? Presumably, the best way would be to give Matlab the values, the row numbers, and the column pointers directly. So basically give Matlab the free arrays it needs to build the sparse object. However, this seems to be impossible. There seems to be no way of actually providing Matlab with these values and then using them to construct a sparse matrix, which is kind of unfortunate because one would expect that to be the fastest approach. Instead, we're left with this second option, which is to give Matlab the values, the row numbers, and the column numbers rather than the column pointers. Basically specifying the sparse object in a column list kind of way, a coordinate list kind of way. So for example, if we want to specify this matrix here, we give a list of the non-zero values, so 11, 21, 42, up to 14. And then for each value, say 42, we provide the associated row number 4 and the associated column number 2. Now, in this case, you can see I provide some additional values as well. In practice, you don't need to do this. However, for certain cases, you should do this. So this value here, this 4, corresponds to the number of rows in our object. This other 4 corresponds to the number of columns, and this 6 to the number of non-zeros. So in this case, we can see from our row index that we have 4 rows, and from the column index that we have 4 columns. However, if we were to have a 0 column at the very end here, so that we would have a 4 by 5 matrix, then this 0 column would not appear in the non-zero values, and therefore also not appear in the column indices, meaning Matlab would not be able to derive that this matrix is in fact a 4 by 5 matrix, rather than a 4 by 4 matrix. So in that case, you would have to indicate that this number of columns is actually 5 rather than 4. Now also for this number of non-zeros, it's easy to see how many non-zeros we have. There are 6 of them. However, if at any point in the future you would like to change one of these values, one of the non-zero values, to a 0 value, so say this 0 becomes a 10, then it's useful to describe beforehand that in fact you want to have 7 non-zero values rather than 6. So by doing so, Matlab will not have to create a brand new array once you change this value of 0 to 10. If you do not specify the number of non-zeros that you desire, Matlab will not have sufficient memory allocated for this new object and will therefore have to copy all this data to a new block of memory, which is going to cost computational time, of course. Now another note on this approach here, you can see that I have sorted my non-zero values in a column major order. If you do not do so, Matlab will still have to convert this to a column major order, meaning that this command may take more time. So if you do not have these values in column major order, this way of building the sparse matrix may not actually be quite as fast. A reasonable alternative in this case is by building the matrix column by column, if of course this approach is possible. So in this case, if you want to build your matrix column by column, so if you have the columns that you want to build your matrix with, you can do so by first allocating sufficient data for the object. So you want to build a 4 by 4 matrix with 6 non-zeros, and then perform a for loop where in each iteration you define the column of the object. So why column by column and not row by row? Obviously, it's going to be because of the column major order in which Matlab has implemented things. So if you allocate your object beforehand using this sballoc, Matlab will know that it needs to create an array of 6 elements. And once you build it column by column, at each iteration, it's just going to append the new column to the previous result. So you start by building this first column, then you append to this second column, which is the value 42. We append to that the third column, and then we append to that the fourth column, building our sparse matrix one column at a time. However, if you were to try the same approach in a row by row fashion, Matlab would have to move the data. So for example, if you specify first this first row, 11 and 14, and then you specify the second row, 21 and 23, then Matlab will have to check that 21 actually appears in column 1 and 23 appears in column 3, which means they appear before 14 in a column major order. So Matlab will have to move the 14 down 2 places in order to squeeze this extra row in there. Then if you specify the new row 33, Matlab will have to check that it appears in column 3, therefore after our value 23, but before the value 14. So 14 will have to move down again in order to squeeze this 33 in there. And finally, if you specify this final row with just the value 42, Matlab will have to check that this value is located in the second column, meaning it appears before all of these 3 values, meaning that this entire object here, this 23, 33, and 14, is going to need to be moved down in order to squeeze the value of 42 in there. So all this data movement is going to cost time, it's going to waste time essentially. So it's completely unnecessary unless, of course, there is no other approach. So this is why you should use a column by column rather than row by row format. Now, for illustration, here's a simple example. So say we are building a sparse matrix with 2000 by 2000, 2000 rows and 2000 columns, and a density of 10%, which I suppose is still quite large, but it's just for illustration purposes. Now we start by allocating sufficient data for our matrix. We are building a random matrix, in case you're wondering. And then we can build our matrix using a for loop, one column at a time, as you can see over here, which is going to cost us about 0.024 seconds of time. However, if we were to try the same approach one row at a time, so building the exact same matrix, but now one row at a time, this is going to cost us about 500 times as long, namely 11.6 seconds. Illustrating that this row by row approach is much more expensive than this column by column approach because of this data movement that has to be performed. In fact, you're going to be better off by performing some smart tricks, namely transposing your matrix. So say that you only have access to the rows of your matrix, not the column of your matrix. So this approach is not possible, say. What you can do is you can build the transpose of your object one column at a time, since each row of our matrix is a column of its transpose. So if we transpose our original object and then build the transpose of our matrix one column at a time, and then finally transpose it back, it's still going to cost us just 0.03 seconds of time, a bit longer than this direct column by column approach, but still much cheaper than the row by row approach. So in this case, it pays to actually look for alternatives that avoid this row operation, remembering that the row operations for these sparse matrices are expensive because of the way Matlab implements sparse matrices. Now, an important note here is that it's not always going to be cheaper to perform transposition, for example. It's always worthwhile to look into alternatives, but don't be surprised if it's still going to be more expensive. Now, what does this mean for manipulating elements of a sparse matrix? So say that we want to set A3, 3 equal to 10. Oh, that's beautiful. Okay, 10. Well, in order to change the value of this element, we first need to locate where it is. Finding the third column is not difficult. We simply look for the third element in our column pointer. Also look at the fourth element, from which we can derive that our third column starts in the fourth position and ends before the sixth position, meaning that position 4 and 5 are reserved for the third column. However, at this point, we need to look through the third row, whether this value is actually non-zero. And if so, change it by this value of 10. But that means that we have to look through this entire column within the row index to find the value 3, and then adjust the value within the value array accordingly. Now in this case, our column has just 2 non-zero elements, so it's not a big deal. But of course, for very big matrices, this is going to be quite an expensive operation. So it's always best to avoid these element-wise manipulations of your object. If you do want to manipulate it per element, it's best, of course, if you can do it per column. So say adjust the third column of this object in one go rather than adjusting each element separately. Now, of course, if your goal is just to change this value of 33 to 10, it's not going to be very helpful to change the third column to 0, 23, 10, and 0. This is not going to be faster than this. But if you also want to change, for example, this value of 23 to say 20, then this is definitely going to be better than performing these steps in a row. These consecutive steps over here. Also important to keep in mind that it's a bad idea to change non-zeros to 0, particularly if you have not allocated sufficient memory. So if you haven't allocated sufficient memory, Matlab will not be able to fit the additional non-zero within the array, meaning it's going to have to allocate a new block of memory that does have sufficient space for the additional non-zero, and then copy everything over to there. So that's not fun, that's going to cost time. But also, if you have allocated sufficient memory, if you are going to change an element at some point after you've built the full object already, it's still going to have to move all the data down according to where your element is located. So unless your element is located at the very end of your array, it's going to need to move everything else down, and all this data movement is going to cost time. So that too is not advised. Now then briefly about permuting sparse matrices, so changing rows and columns, for example. This too is going to cost, it's going to be quite some data movement. It's going to require finding what elements occur within a particular row. So for example, say we want to change rows 2 and 3. We can do that by specifying this command there. We can see that we exchange rows 3 and 2 and keep the columns the same. Now obviously this kind of operation is going to be more expensive than the column-based equivalent, simply because of this column major order in which Matlab implements things. But both approaches are not really desirable. There is, of course, the alternative of multiplying your matrix with some permutation matrix. So pre-multiplying it with a permutation matrix to exchange the rows, and post-multiplying it with a permutation matrix to exchange the columns. But in general, this approach is going to be cheaper if you do really want to permute the object, if you do want to exchange rows or columns. Except if you have this permutation matrix already, it may not be cheaper to find the associated array. in this case, so then perhaps this multiplication may be faster than trying to find this array first and then perform this operation. Otherwise, though, this approach is slightly better than this approach, though if you can do it in a column-based format, that may be beneficial. Now, since we're talking about exchanging rows and columns, let's talk a bit about transposition. So an interesting fact about the compressed sparse format is that if we have an object A, an array A, described in compressed sparse row format, then we can actually describe the transpose of this object in compressed sparse column format using the exact same arrays. That is, the value array is identical, the row index is identical, and the pointer is identical. The only difference is that here we're using row index rather than column index, and here we're using column pointer rather than row pointer. But other than that, the values themselves do not change. So what this means is that if we want to transpose a matrix A in Matlab, all we have to do is change the compressed sparse column column format to a compressed sparse row format, and then basically we have the three arrays that we need to describe the transpose in a compressed sparse column format. However, converting a compressed sparse column format to a compressed sparse row format is not a cheap operation. It basically involves two steps. First, we have to convert the column pointer to a column index. That's not a particularly big step. But then we need to convert the row index to a row pointer and also adjust the value at the same time to be in a row major order rather than column major order. As I mentioned, this first step of converting the column pointer to a column index is not that big a deal. We can check from the column pointer that our first column is going to start in position 1 and going to end before position 3, meaning that we should have 2 times the first column will appear. The second column is going to start in position 3 and end before position 4, meaning there's only room for 1 element in column 2. Then the third column is going to start in position 4 and before position 6, allowing 2 elements in the third column. And then finally, our final column is going to start in position 6. And since we have 6 non-zero elements, there's only going to be room for 1 non-zero element in the fourth column, meaning this is going to be our column index, as you can see over here. Now then we basically have our object in a coordinate list kind of manner, but converting this to a column major, compressed sparse row format is still an expensive operation, simply because the value is now still in a row major order, whereas we want it to be in a it's in a column major order, but we want it to be in a row major order. So that's going to require looking through the entire row index to find which values are located in each row. So for example, for the first row, we need to look through the entire object to find that in fact the first element and the last element are both located in row 1. Now doing this for each row is going to be quite expensive, and then ordering everything to be in the row major order with an appropriate row pointer is not particularly cheap. Now Matlab has implemented a reasonably efficient way of doing so, of course. We don't have access to the source code, so we don't know exactly what this looks like. But you can imagine that it's not a particularly cheap operation, and therefore if you can avoid it, you should. Now, why am I mentioning this? Simply because I showed you earlier that transposition can help you out if you want to avoid the row major orders, so row major operations. In order to save some time, then transposition can help you out there. But don't be surprised if the transposition is going to cost you more time than it saves you. That might appear in certain situations, simply because the transposition too needs to adjust, look through these rows, adjust them in order to get the values in an appropriate manner. So that too may cost a bit of time. A final thing I would like to discuss is just operations on a sparse matrix. Obviously, since Matlab is built in a column major format, operations are also performed column by column, meaning that, for example, this operation is going to be cheaper than this operation. Right here, we're concatenating the columns of two objects, whereas here we're concatenating the rows of two objects. So obviously, this is going to be much cheaper than this. Similarly, if we're multiplying a matrix with a vector, that's going to be more expensive than multiplying a vector with a matrix. That's because here we are multiplying each row of A with one column B, whereas here we're multiplying one row with each column of A. So in this case, it may actually be cheaper to perform, say, C is B transpose A transpose transposed. So if you want to perform this operation, it may actually be cheaper to do this, though that will depend on the exact situation, of course. But it may be cheaper simply because here we're multiplying in a column favorable order, which does not occur over here. All right, so that's basically all I have to say. Just a brief summary here. If there's anything I would like you to take away here, it's that Matlab stores matrices in a column major format. And that means it stores sparse matrices in a compressed sparse column format. And it really influences everything else. All the operations in Matlab are based on this ordering. So that means that if you can, you should work with skinny rather than fat matrices, lots of rows rather than lots of columns. Also, you should limit direct adjustments to the matrix. This CSC format is really not built for a lot of adjustments to each individual element of the matrix. So if you can avoid that, then do so. If you cannot, try to do it one column at a time, of course, rather than one element at a time or one row at a time. And also limit row major operations. So the arithmetic in Matlab is quite efficient. However, if you can look for alternatives like this one, they may be cheaper than, say, the row major operation over here. Though, of course, always keep in mind that it may also not be cheaper. So it's worth looking at alternatives, but it's not always going to pay out as well. And that's all I have to say. Thank you very much for your time.